So what I want to do is just kind of set the general stage, and I might even write this down if for no other reason than that way I'll remember that I said it. Here's kind of how we've been thinking about these kinematics problems. All right, we started with one-dimensional kinematics. Those were problems where we had some information about an object that was moving, but it could only move one way or in the exact opposite direction. And then we introduced the idea of 2D kinematics, two-dimensional kinematics, where we have motion that we are thinking about as occurring in one axis while simultaneously occurring in another axis that's at a 90-degree angle to the first. And because of the magic of physics, motion in one of those dimensions has no impact on motion in the other one. And so what that allows us to do is mathematical trickery to deal with things that are moving, say, along a curved path. We can think about its motion along one axis completely separately from its motion along the other axis, which means we're taking complicated motion and turning it into two simpler problems. One in one dimension, another in dimension that's at a 90-degree angle to the first. And if we do that, then we can make all sorts of predictions about how objects will move in two-dimensional space. There's a couple extra steps, but it's not too challenging. And we've looked at a couple different levels of this. The first level is the simplest kind of two-dimensional kinematic problem, which is a projectile launch, where we know the initial speed, we know the height above the ground, and we know that it's a perfectly horizontal angle, and we use that information to predict how far the projectile will go. And then we added to that an angled launch. That's what we've done so far. My expectation at this point is that you all can do the first. That if I were to give you conditions, you have a launcher that's fires at 6 meters per second, it's a perfectly horizontal launch, it's 2.5 meters above the ground, how far will it go? You should be able to do that. If you can't do that now, we'll help you, but get on it, because at this point that is a must know. The second one is a little trickier, because this angled launch gets into this idea of looking at quantities that are neither horizontal nor vertical, but they're at some angle. And then in order to use those with our two-dimensional kinematic trickery, we have to first figure out how much of that quantity is in one of our dimensions and how much of that quantity is in the other of our dimensions. And what's really tricky about that is that that's not real. I mean, objects are only moving in one direction. They only have one acceleration. And so when we think about like, well, this velocity has two parts to it, that's not really true. It's just, we can work with it mathematically, but it gets tricky to try to visualize what's going on when we take one quantity and break it into two imaginary parts. Yeah?
Just to be clear, when you talk about deducing distance from those pieces, and you say that's a must have, you don't mean that the formulas and you still
Correct.
Correct.
Correct, yes. So the question was, do we need to have the formulas memorized? No, you don't. Even for AP students, you will be given the formulas. In the regular class, you'll never need to have those formulas memorized, nor will you need to be able to apply them because you'll always have access to the solvers. But in AP, you'll need to be able to do some basic math to arrive at answers. It won't be super complicated. They won't be giving you problems with lots of decimal points and stuff, but you'll need to be able to plug some numbers in and get answers out of it. Yeah. Okay, so these are sort of the simplest cases. Horizontal launch is the easiest. Angled launch is a little bit more complicated. The next step that we're going to go to is projectile launches, where we're predicting other things. So if we think about like what we've done so far, it's always been the same question. How far will it go? How far will it go? How far will it go? But yesterday what I showed you is that if we think about the path a projectile takes, if we know these initial conditions of speed, height, and angle, the whole path is predictable. Where it's going to be is predictable. When it will be there is predictable, which means we can answer more questions than just how far it's going to go. We can answer questions like, how high will it go? What will its speed be at a certain spot? If it moves this far horizontally, how far up or down will it have gone? How long will it take to go up this high or to go down this far? Those are all questions that we can ask. That is still using this essential framework of a projectile launch with 3 basic pieces of information. Something about the speed, something about the height, and something about the angle. And that is as far as we're going to go with projectile motion. And we're going to work on this for a couple more weeks, and then we're going to move on to some other stuff where we start talking about forces. When we talk about forces, we're going to add a 3rd level, which is general predictions. And with general predictions, we can do all sorts of stuff. If, for example, we launch something from a projectile launcher, and we know how high above the ground it is, and we know how far it's gone, and we know the angle of the launch, we can figure out what its launch speed was. So we don't know what the speed was, but we can find it out. We can sort of predict in the past, right? Like we can make a prediction in the past. Or if you tell me how far a projectile goes and how high it gets at its maximum height above the ground, I can tell you how quickly it was launched and what the angle was. Like there's all sorts of predictions that we can make that don't just involve knowing these things. It's not like there's one kind of problem where you know this and this and this, figure out the answer. And then there's another kind of problem where you know this and this and this, and you figure out some other answer. And you know some other kind of problem where it's this and this and this, and you find some other answer. Instead, what I'm going to lead you to is the idea that we're going to use the exact same framework to solve all of these problems. It does not matter what the initial measurements are, nor does it matter what the predictions are. The process ends up looking the same every single time. And there's a bunch of tricks to it. So there's going to be times when you're like you're going to get stuck, and then I'm going to explain, oh, well, here's the trick for this one, here's the trick for this one. The process, though, is the same every time. And that's what I want to emphasize when I solve this problem, because this is different. You haven't done this one before specifically, but what you'll see is, oh, I get it. It's the same process. The process looks the same no matter how we do it. So I'm gonna go through this, and I'm gonna explain how I'm following each step of the process. The first step is always draw a picture. So it says, at a football game, an air gun fires t-shirts into the crowd. The gun is fired at an angle of 40 degrees from the horizontal with an initial speed of 28 meters per second. So here's the gun, it's on the ground, and it does not say like how high up it is. And this is one where if I were to give you a test, which is not going to happen unless you're in the AP Physics class, but if you are in AP Physics, I will give you tests. I will be more clear about this. But in this case, we are to assume that the t-shirt starts on the ground. Starting position vertically is the ground. It doesn't say that specifically, but that's the assumption. It gets fired off at an angle like this. And I drew an arrow here. That arrow is an arrow. It's not a vector. We can't draw vectors. We can draw arrows though. And this particular arrow is going to represent my velocity of the t-shirt right as it's fired from the gun. It has a velocity, which means we're talking about a vector quantity that has both a magnitude and a direction. The magnitude is 28 meters per second. So at the moment it leaves this launcher, it is moving at 28 meters per second. It is moving that fast in this direction, 40 degrees up horizontally from the ground. One of the things that we haven't talked about yet, but we will, as we start solving more complicated problems, not with the projectile launcher necessarily, although it probably will come up. But a lot of times people are like, okay, well, this arrow represents the velocity vector, so that means it moves like this, right? Like we sort of assume that it sort of moves along that arrow. But if we were to draw the path of this projectile, what you would see is it actually doesn't. It never touches this arrow. It's only in contact with the arrow, conceptually, at the moment of launch. The t-shirt has this position right here at the moment of launch, which happens to be where I've drawn the end of this arrow. If we were to look at the path of the t-shirt, it starts accelerating downward immediately, which means it falls away from the arrow. The arrow isn't real. The arrow is an indication of the initial speed and direction. The arrow doesn't point to anything meaningful. Its length doesn't signify anything meaningful on this diagram. And we don't say the t-shirt goes from here to here, or we don't like say, well, this is going to point at the highest place that the t-shirt goes. None of those things is true. This arrow simply tells us the direction of this object's motion at the start of the problem that we're considering. And as soon as it starts to move, it changes direction. If we were to visualize its velocity vector as an arrow, we would see that velocity vector rotate so that it was pointing downward. Pointing up and to the right now, it's going to point lower and lower and lower. Here, it would point completely horizontally. Now it starts pointing down. Yeah?
Theoretically, if the camera were at a 90-degree angle, would it follow the arrow?
Yeah, if we were pointing straight up, it would follow the arrow, but that's not a cause and effect. That just has to do with the acceleration. Right? If there were a different acceleration, it wouldn't necessarily follow the arrow. But in this case, there's no horizontal acceleration. That means that if you shoot something perfectly vertically in a perfect world, and it doesn't accelerate horizontally, then its horizontal velocity will never change. It started at 0. So you have one-dimensional motion. And in that case, the arrow will point to where it's going, and then it'll point in the opposite direction of where it's going as it comes back down. Okay, so let's keep working here. And then a fan who is sitting 60 meters horizontally from the gun, but high in the stands, catches a t-shirt. So we don't know exactly what this is going to look like, but it says high in the stands. So let's assume that it's like this, right? Like the fan is kind of up here. I don't know. It may be that this thing is still going up when it gets to the fan, or it may have gone up and started to come back down. All we know is that this distance right here is 60 meters. And then there's two questions. One is, how long does it take the t-shirt to reach the fan? And the second is, at what height is the fan from the ground? And we don't care about either of those questions. If you use the system, the framework that I've given you, you'll realize the specific questions they ask often are just red herrings. They're designed to kind of make you confused about what it is that you're trying to do. What you're trying to do effectively is, using the information that you have, predict as much as you can about the path of this projectile. And in doing so, you will discover all the possible answers to all the possible questions that anybody could ask with this initial set of information. Okay, what do we know? Speed, we know angle of launch, we know how far it goes horizontally. With that information, we can find the path that this projectile took, and we can figure everything else out from there. So that's all the information given in the problem. The next step, establish a reference axis and the origin in both dimensions. So in this case, it makes a lot of sense, since we know, or we're assuming the t-shirt starts on the ground. We're going to say the location where the t-shirt starts is 0, 0. We'll have our reference axis be up is positive, to the right is positive. This isn't always going to be the case, by the way, and I will tell you when we get there how to know when you use this reference axis versus some other one. And the answer is, We just pick whatever's gonna make it easiest to solve the problem, and there's some simple ways to do that, like just some questions that you'll ask yourself. And as soon as you ask yourself those questions, you'll realize, oh, I'm gonna use this, or I'm gonna use this, or I'm gonna use this. So it's pretty straightforward, but for now, it's always gonna look like this. The next question is sort of a new one. It has to do with the whole angle thing. And that question is, this is in our framework, are there any quantities that are vector quantities that are not aligned with our set of reference axes here? And that's weird because I told you that that's the question that you're asking, but what does that mean? What does that actually look like? Like, are there quantities here that aren't aligned with this reference axis? How do you know? What's a good way to tell? Does anything scream out to you like, well, that's not lined up? Anybody see anything that like jumps out? You do, don't you? I mean, not you personally, but some of you do, right? Do you see anything that obviously seems that it's sort of at odds with this?
A 40-degree angle?
Yeah, a 40-degree angle. So how do you think about that? What I do when I'm thinking about vector quantities and a reference axis is I draw them together. I know that this is my reference axis. How do I know that? Because it's always going to be our reference axis for now. So you don't have to worry about, like, should I use something besides this? Just use this. Up is positive, to the right is positive. Perfectly horizontal is our x-axis, perfectly vertical is our y-axis. And then draw an arrow that represents the vector quantity in question. In this case, we have information about velocity at an angle. So a 40-degree angle looks about like this. I'm just going to draw an arrow. Is that the vector? No. Does the length of this vector tell us how far anything is moving? No. This is just an arrow that is telling me that there's a quantity in this direction. How big is that quantity? It's 28 meters per second in magnitude. It's not length. This vector doesn't have a length, it's a speed. How long is 6 miles per hour? It doesn't make any sense. The arrow has a length, but that's not a vector, that's an arrow representing a vector. The length of this arrow can represent the magnitude of the vector. So I would expect if there were another vector quantity of velocity and it had a magnitude of 14 meters per second, that it would probably be drawn about half that long, because that would make a lot of sense. The angle, the direction of this vector quantity is 40 degrees. So what is that telling us? Because we know, like, ultimately what we're going to be doing is making a variable inventory with x's and y's and accelerations. And so one of the things that we want to know is, well, wait, are we talking about, this is like initial velocity, it says that, it says something about initial velocity, but which of these two initial velocities is it? We have two initial velocities, but we don't. We only have one initial velocity. This thing is moving with a certain speed in a certain direction at this time. That's one velocity. When we look at this quantity, Vx0, and this quantity, Vy0, what we're asking is how much of this object's initial velocity is in the same direction as our x-axis, and how much of this initial quantity is in the same direction as our y-axis. Vx with a 0 and Vy with a 0 are pieces of a whole, okay? In this case, the whole is what we would just call the initial, oops, that's not writing, the initial velocity. It's not in the x direction because it's not perfectly to the right or perfectly to the left. And it's not in the y direction because it's not perfectly up or perfectly down. It's in this direction, 40 degrees up from the horizontal axis. Sometimes we think about negatives as direction, right? But negative and positive only have meaning if we know an axis. Like if we say, we're talking about the y-axis, as I have it drawn here, then positive is up and negative is down. If we say we're talking about the x-axis, then positive is to the right and negative is to the left. What would negative 28 meters per second at a 40-degree angle mean? Because that's kind of two directions at once. Negative we're using as a direction, but 40 degrees is a direction as well. Would it make sense if I told you, hey, go 10 feet northwest, go 5 feet south to the east, go negative 5 feet north? What does that mean? Those are two different directions that you can't really put together. So one way to think about, like, if we had a negative sign here, one way to think about it is, that's not meaningful. Vector quantities have a magnitude. This vector quantity of initial velocity has a magnitude of 28 meters per second. It also has a direction. That direction isn't positive or negative because it's not moving only along one or the other axis. Its direction is this number right here, 40 degrees, up from the horizontal axis. That tells us the direction. A slightly more complicated but mathematically correct way to think about it is, if we put a negative sign in front of here, it would be in the opposite direction. So 40 degrees with a positive quantity is up and to the right. 40 degrees with a negative quantity would be down and to the left. Mathematically, that's how it works. We have defined an axis here. That axis is at 40 degrees to the horizontal. Positive directions along that axis are up and to the right. Negative directions are down and to the left. But typically, we won't use negatives when we talk about quantities that are not aligned with our axis. Okay, so we have correctly identified that there is a vector quantity that's not either perfectly horizontal or perfectly vertical. So how do we deal with that? We use the vector solver. So we'll plug that into our vector solver. The magnitude was 28, the angle was 40. It's pointing up and to the right the way I've drawn it. And that gives us an x component of about 21.5 and a y component of about 18. So what does that mean? That means this much of this overall velocity is just to the right. 21.5 meters per second of it is just to the right. And this amount of it, 18 meters per second, is just straight up. That means that since this is our overall initial velocity, this piece right here is our initial velocity in the x direction. And this piece right here is our initial velocity in the y dimension. So we found the parts that add up to make this overall quantity. Is it really moving with two different velocities at the same time, or three? No, it has one speed, it has one direction at an instant. But mathematically, we can think of that one speed as having two parts that are at right angles to each other. And because we can do that mathematically, we can employ physics magic to solve this problem. So now we have some more information. We know this thing starts at position 0, and we know that it travels 60 meters in the horizontal dimension, so its final position is 60. Its initial velocity in the x dimension is 21.5 meters per second. We are assuming, since this is projectile motion, that there's no acceleration. So that means that the final velocity will be the same because the acceleration is 0. Its initial y position is the ground, which is 0. The final y position, with wherever the fan is, the initial speed in the y dimension is 18 meters per second, positive because it's up. We don't know how fast this thing is going once it gets to the fan. When the fan catches it, it's going to stop. But the acceleration won't be constant anymore. So what we're really looking at is how fast is it going right before it touches the hands of the person who catches it. The acceleration is negative 9.8 meters per second squared. And here's where it gets interesting, because prior to this problem, we've kind of approached these the same way, which is, well, we start over here and find time. And then once we find time, we can find final position. But this time, we already know the final position, so we don't need to find that. And if you look at our kinematic equations or use the solver, you'll realize we do not have enough information to find time over here. So this is where we come back to the idea that the framework doesn't say, try to find the answer. The framework says, what can you figure out? You can't figure out anything over here. But guess what? We have enough information in the horizontal dimension to find how long this thing is moving. We didn't in the other problems that we were doing, but in this one we do. So let's put it into the solver and see what we get. We have an initial position of 0, final position of 60. My speeds are 21.5 and 21.5. There's no acceleration, and I want to know how long is it going to take. And this is the equation that has all the variables that I've got in it, and the answer is about 2.8 seconds. It's going to take this t-shirt about 2.8 seconds to travel this horizontal distance. And during that time, it's also moving vertically. It goes up, and maybe it comes back down. We don't know. But if it moves 2.8 seconds in the horizontal dimension, then it has to also be moving 2.8 seconds in the vertical dimension. You don't get to move only in one dimension while time stays still in the other. So now we have more information over here. With this information, we probably could find final velocity. In fact, I know we can. And this is where maybe you do, right? But most of you would probably, at this point, be able to say, oh, what we're trying to figure out is how high up above the ground this person is. That's gonna have something to do with my, Y position. It's really this that we're looking for here, the final Y position. So if we put all this information into the solver, we're gonna determine that with an initial position of 0, an initial velocity of 18, an acceleration of negative 9.8, and a time of 2.8 seconds, we can find the final position. These all say X, but the kinematic equations there's no magic in the variable that you're using. I'm using these for my y-axis, so these are y values. This is a y equation that I'm using, and my final position in the y dimension is going to be about 12. So that means that this is about 12 meters. And I don't even know if that's right, by the way. It looks like it's right. I see at 2.8 seconds for how long it takes the t-shirt to reach the fan, and I see 12 meters for a possibility for where the fan is, so that's probably right. I might have made a mistake. It doesn't matter. The process is the same. And interestingly, we solved this, even though we were looking for something different, the same way in general that we solved the other problems. And that's really the big key, because what's going to happen as we start adding complexity is that you all, very understandably, are going to be asking questions like, well, wait, how do I find final velocity? We haven't done that before. How do I find acceleration? And the answer is, draw a picture, frame of reference, identify quantities that need to be broken into vector components, make a list of your variables, and then just start finding stuff out. And eventually, you'll get the answer. It works every time. All right.